Hey everyone, great to see you. What I'm going to talk about today is compute over data in 2023. So I want to focus on the impact that we can have next year. I'm going to talk about, give a quick introduction to kind of at a larger macro scale, give a sense of a range of projects and kind of the moment that we're in now and what we're likely to see in Q1 and Q2. I want to talk about why there's very likely to be many different compute networks, and then how that breaks down into many different interconnecting projects. Then from there, I want to talk about some early applications that I suggest to you as good things to kind of get started with. And then I want to kind of articulate why we want to focus on having like strong early impact and how to build on that. And then I want to do some Q&A. So many of you have probably heard me say this already, but Web3 is not yet web scale by any means. When you think about the web and most of the applications that we use day to day, we're thinking about massive scale systems with trillions of transactions and so on, with massive scale of data and compute and so on. So Web3 is very far away from this kind of setting. At the same time, the benefits of Web3 computation, which is public verifiability and decentralized decision-making around systems, or building public utilities that anybody can leverage without having to trust human contracts in specific jurisdictions and so on, all of those benefits haven't yet come to computation. And because of this problem, Web3 is also kind of stuck in Web 2.5, where there's a lot of applications in Web 3 that end up having to revert back to Web 2 because you can't actually have backends in kind of this Web 3 setting. And I'll dig it a little bit into why that's actually really hard in a bit. So when the Falcon project, this is kind of the broader plan of the project, where in step one we're amassing a massive, large-scale decentralized storage network. We've mostly accomplished that. In step two, we're onboarding massive scale data from a ton of applications and systems and so on. And in step three, we want to bring computation to the data. So primarily today is going to be kind of about step three. But just to give you a flavor of the scale here, the network has amassed close to 17 exabytes globally with a ton of GPUs ready for computation, which is pretty awesome. So there's a massive scale network with GPUs there ready for your compute networks to deploy jobs to. And there's a ton of data that is being added where a lot of the users of this data want computation to be added into this. And because a lot of this data is public or kind of public commons type data, there's likely to be many more users of that data than the original parties that may have wanted this data backed up. So it's an environment ripe for compute over data systems. There's a lot of kind of on-ramps that are bringing different kinds of data, and this is driven by an economic component of Filecoin called Filecoin Plus that's kind of bringing a ton of data into the network. So this means that Filecoin is a great target for compute over data networks. Now, a bunch of the data sets that are being added, like I mentioned, have this kind of public data commons orientation, but in particular, the needs there are around the traditional style data science pipelines. So this is not, you don't need kind of real-time computation, say, for something like a social network where you kind of send out a tweet or upload a video and you need like super fast, super responsive communication. You can actually lean on asynchronous large-scale data pipelines and the traditional kind of data science type jobs, which is a perfect fit for where we are in compute over data. One other component that's going to arrive in kind of that's launching now and will get better throughout next year is retrieval. We want to get to kind of sub-second retrieval of all of the data on Filecoin. Now, you probably have heard a lot about IPM, and you will hear a lot more about it until it launches. This is going to enable a lot of these compute over data networks to be deployed into Filecoin. And I'm going to dive into this in a moment. So again, like the hardware is there, ready for compute over data. The data is there and growing with a lot of different kinds of users. And now what we need is to build the computational networks to be able to leverage that data and create that value for users. Now, if we do this right, then we can properly make Web3 web scale, and we can imbue the day-to-day applications that we use with public verifiability and the utility of Web3. So I'll make briefly the case about many networks. So there's a lot of different types of cryptographic primitives when it comes to verifiability and privacy. And when you're in the decentralized setting, you cannot trust the computer. You cannot trust the computer to actually do the job. You cannot trust the computer to not leak the data. And so verifiability and privacy become way harder than in the centralized cloud. Now, in reality, you can't actually trust the centralized cloud either, and that's part of the point, except that the centralized cloud has been, so far, riding on this kind of brand game and contracts and so on, and that has mostly worked for a large set of applications. But it kind of breaks down when you enter different settings where computation is kind of important kind of on a national scale, or where you want to build robust systems that can resist massive scale attacks and so on. So all of these, there's a lot of different approaches to achieve verifiability in this public setting or achieve privacy in this public setting, but all of those approaches have different trade-offs, have different characteristics in terms of performance, and sometimes conflict. You might lean on an approach towards verifiability, and that pushes you away from privacy. It makes certain kinds of privacy harder. Or you might push towards privacy, and that just makes it way harder to make it verifiable. So unfortunately, we have this very hard set of trade-offs for decentralized computation that makes it difficult to land on this. Now, how do we navigate this? Well, what's likely to happen is that this is going to yield many different projects that tackle these different spots in the design space and build different networks. Different technologies will appeal to different use cases. Those different use cases will mean different customers. Those different customers will require different branding. That different branding will mean that different groups and different projects will appeal to that set. So we're likely going to end up with many different networks that are doing computation in this decentralized setting. Now they're going to need to interop. They're going to need to be able to kind of work over data in the same kind of environment and so on. And if this kind of model is not convincing enough, then just look at the current cloud setting. Already in these large-scale systems and large-scale brands, you end up with many different sub-products that do different kinds of computation and different kinds of processing and so on. So whether these kind of later down the road get sort of unified in kind of porcelain-style products at the top, it's a separate question. Either way, right now, for the next 2 to 3 years, we're very likely going to end up with many networks. And so the Falcon network, because it has the large-scale data capacity and it has a bunch of the hardware already, is a really great target to be kind of like a home L1 for a lot of these decentralized compute networks. And even if it isn't kind of the root of that network, even if it might be home somewhere else, say Ethereum or some other network, can still leverage all of the data on Falcon and all the computation primitives of Falcon. Cool. So in a sense, you can think of Kubernetes as the kind of poster child of scheduled computation in the decentralized cloud setting. Now, there's many different approaches to this that have been tried over many decades, but this is kind of roughly how things look. You have some cluster of machines. You add a program like a kubelet or a borglet or whatever. You coordinate these by talking to this kind of master scheduler, and then users submit jobs to this scheduler. The scheduler then sends the job over to the worker node. The worker node processes the job, then submits the results back to the scheduler, and then things go back to the user. Now imagine kind of replacing that scheduler. Instead of it being a specific machine, you can put that into a blockchain directly. You can run the scheduler in a blockchain, and you can maintain that in a smart contract. That's kind of one of the settings that you can explore. And if you need really high throughput scheduling because you expect millions or billions of jobs, don't worry. Blockchains are scaling. There was a whole other summit last week right here talking about how you can now get blockchains to be able to scale, to be able to handle that kind of thing. But the point is that you can run a scheduler in that setting, and you don't have to treat that as an additional kind of single point of failure, and so on. Now, the Bacalao project is already doing a ton of this. I don't think there's yet a scheduler on chain and so on, but that's kind of likely to come in the future. But either way, whether you use a scheduler on chain or in a different node and so on, you have this really nice setting where you can kind of think of all of the computation and all of the data as addressed by CIDs, content addressed, which is a really key primitive, which, by the way, offers tons of benefits besides all the decentralization of the networks, right? Being able to address your computation with hash linking, or being able to commit to the data and memoize computation, and all of that, you get all of that for free when you use hash linking in the way you express the compute jobs, in the way you express the data, in the way you do intermediate computations and so on. So aside from all of the Web3 benefits, just that alone, being able to have a hash-linked oriented compute network is super, super, super valuable. And so that's where we can create a lot of utility. So now think of being able to implement the things on the left, like these kind of Kubernetes, Lambda, Cloudflare Workers type things, with some of the kind of primitives, and bring some of the primitives on the right, like things like verifiable computation, things like fully homomorphic encryption, and so on. This is where all of this stuff is headed in the long term. Now, it's not going to kind of land there in the short term because these things are pretty expensive. Fully homomorphic encryption is still very expensive, though you'll see that starting to arrive over time. Now, in order to kind of do this, there's a ton of work that we have to do in kind of the underlying plumbing that all of these decentralized networks, decentralized compute networks, are going to have to do. So things around kind of how do you architect the thing, how do you blend it with different programming languages, how do you kind of write libraries for all of those programming languages, how do you, what VMs do you use, how do you encapsulate, what kind of program formats do you use, how do you compile all the things? How do you schedule the things? What are the scheduler? What are the features of the schedulers take? How do you monitor your system? How do you kind of extract information about the system in terms of what's going well, what's wrong, like where is your pipeline stuck? How do you do I/O of the data? Like how do you have to specify the formats ahead of time? What kind of ETL do you have to do to the data ahead of time before you can run your own code? And then kind of what does the UX look like for the people running the worker node? What does the UX look like for the developers that are trying to use this, or the end users, and so on? So there's an enormous amount of work that is involved with running any kind of decentralized compute network that everyone's going to have to do. So what are we doing? We're saying, great, a bunch of this stuff is common stuff that everyone can leverage, and so let's solve it together. And then that'll become a really great basis for being able to derive specific decentralized compute networks that tune for a specific use case. So think of that as being like a really good platform that everyone can just kind of use an open source project to then derive some more specific computational network, which then you then tweak and tune. What you change the scheduler, you change the verification, you change the deployment pathway, you change the use cases, whatever might be specific to your case. But we can all collaborate on making the common parts really good. This is kind of like similar to kind of the IPFS and Filecoin kind of trade-off, where you can have a kind of fully open source project that doesn't say anything about how you pay for the thing or where do you run it or where the context is, but has all of the tooling for how do you address data, how do you move data, how do you address the computation, all that kind of stuff. Cool. And now, so probably a lot of you will either be building applications on top of decentralized compute networks, or and want to leverage that utility, or potentially will be building decentralized compute networks yourself, and you will be building one of these networks and launching it and so on. So for that, I want to plug some resources for builders. There's a whole series of hackathons that can help give you kind of good opportunities for you to go and build the stuff. There's micro grants that can help you get started. There's requests for startups that can kind of spark new ideas for new business models that you might leverage. So all of this stuff is there. And then once you kind of start finding something significant and you start scaling it, there's things like accelerators and VC funding and network capital funding in our ecosystem that can be helpful to you. So strongly encourage kind of looking for these things. If you want more info about this, there's we gave a summit last week on Monday, the PL Summit, that kind of describes this stuff in detail. Great. So there's going to be a bunch of networks and a bunch of users on top of them. Now let's talk about some of the projects that are ongoing right now. This is kind of the R&D pipeline with a lot of stuff going on and translating from research all the way into development and production and use. I mentioned before the Falcon project and the storage providers and so on. Think of kind of the life cycle of data moving in the network, where there's some clients that are kind of onboarding data into storage providers, and then they're retrieving it. That data gets indexed by a set of indexers to be able to look it up really quickly. But computation permeates the whole network. So in particular, you might have massive scale computation in the storage providers. So this is where you have data center level quality deployments with tons of GPUs and so on, and potentially dedicated hardware. We might start to see specific computational networks demand specific types of hardware that accelerate zero knowledge or accelerate fully homomorphic encryption, and you can deploy those in those kind of storage providers very close to the data, right? So you don't want to move the data. The data is enormous. You don't want to kind of move petabytes. That's very expensive. You want to move the computation and the hardware, which is way cheaper to move, to where the data is. So that's kind of like why kind of we tend to say that Filecoin has gravity, or that data has gravity, where over time the data sort of accumulates into source providers, and you want to move computation and the hardware to the data. Now, you might also want to run some computation in larger scale networks that are close to the edge. So think of like the Cloudflare worker setting, where you might have a very large network of kind of computers in ISPs or computers in homes and so on, where you have a ton of processing power, because by the way, like these phones, like a pretty powerful, and when you're plugged in at night, you could actually use them, or your laptop or your desktop machine and so on. You could use all of those nodes also for computation. You just need to kind of orchestrate them, and you have to figure out solve the UX problem to enable the users to use them. You have to think about like policy settings, where like what kind of computation can run where, what kind of resources are available. So a bunch of hard problems about how to schedule this right, which by the way are again common to everybody. So let's sort of like solve them together. And that's where kind of Bacalhau and Station come in. So there's two projects here that are going to be extremely, extremely useful for everybody. So first off, Bacalhau is solving a ton of the problems for how do you create these kinds of networks, and how do you organize them, how do you build tooling to be able to ingest various kinds of data and so on, how do you model the computation, how do you run it, and all that kind of stuff. Station is a project to be able to kind of build this kind of thing you install once, and you can run many jobs for many kinds of networks. So the kind of like UX of Station is that you download one program, you run it in your computer or in your server, or eventually later your phone and your browser, things like that. And then that kind of profiles your device. You set some policy about like what can or should be able to run there, or what kind of resource utilization you expect. And then Station kind of figures out like what is the best thing to run based on your profile, and can run many kinds of jobs for many kinds of networks. It could be running jobs for a CDN, it could be running jobs for a compute over data network, and so on. So think of like Station and Bacalhau being like really good fits. And then there are things like the Falcon virtual machine and the IPVM, the FVM and IPVM that are going to be really useful as components in building these much more specific decentralized compute networks. So yeah, you've probably seen a lot about FVM. You heard about IPVM earlier this morning. Heard about Bacalhau. I don't know if you've heard about Lurk and Zama, but these are kind of the zero knowledge computation, or in Zama's case, fully homomorphic encryption. Cool. So think of like all of these projects sort of interconnecting to be able to give you this like really nice substrate where you can create specific, kind of specialized decentralized compute networks, or where you can kind of, as a user, use these networks to kind of leverage the utility of the broad network. And you can think of different deployments, right? So your application might want to run large-scale computation in a data center setting because you're processing tons of computation, or you need kind of a ton of GPUs or something like that. You can lean on that set of users. Or you might want a very wide distribution of users around the world because you're doing something more interesting that involves networking. So you might need to use nodes in the spread out around the world and so on, and that's kind of like where the kind of virtual provider type setting helps. Or you might actually want to push some of the computation all the way to the user's machine. There are some kind of edge or kind of full local-oriented computation things where that becomes relevant. Cool. So let's talk about some early applications. So right away, there's a ton of different use cases in Web3 that require computation. Building good bridges to a bunch of the other networks will help a lot with that. So being able to kind of do a bunch of the compute-oriented jobs that all of these networks require, like that would be really great. It would be also awesome to shift a bunch of these systems from Web 2.5 fully into Web 3, because again, a bunch of these things are kind of bottleneck for not being able to run because of verifiability or privacy reasons. I think video is going to be massive in 2023 and 2024. But, maybe it'll start kind of growing in 2023, and then it'll become massive in 24, 25. But this is where kind of things like transcoding, and this is a slide from LifePeer, which is a video pipeline processing network, and that's where think of all kinds of applications related to video that could be running. Remember that video is one of the largest use cases of computing and networking in the world. It's a huge fraction of the bandwidth used every year. It's a huge fraction of the storage. And so think of tons of processing involving video. And that's likely only going to increase. And it's going to get messier with AI, right? Because now AI can generate tons of video, so that's going to get fun. All kinds of like media processing pipelines. I'll mention kind of decentralized science, because this is a use case very near and dear to us. It's kind of where IPFS came from and so on. DeSci is a movement to improve science using Web3 tech and tools. Think of everything related to open access papers and open access data, being able to run, store all the data together, being able to run computations on that data together, being able to have reproducible science where you can kind of understand exactly what the computation was that was done over the data to get the results. All of that is kind of accessible. You have containerized programs, you have VMs and so on that you can run and reproduce all of the results and figures and so on. So being able to kind of imagine a lot of this tooling being used to improve science. So this is a great area for kind of early applications. You can think of building kind of like a GitHub for Science type of tooling. I don't think we should be building a specific platform that is a GitHub for Science. I think that's unlikely. For a lot of reasons, I don't think that's the right fit for science, but think of all of the primitives and components that might be involved in a GitHub for Science. Think of all the analogs to versioning and addressing and pipelines like CI and all that kind of stuff. And in terms of reproducibility, this particular problem is pretty large. It sounds kind of, for everybody coming from computer science, it sounds kind of simple, like, oh, virtualization is kind of old news, 1970s, 1980s. Why is it so hard? In reality, it's pretty hard because people write programs in a bunch of programming languages that rely on kind of the latest versions of things, rely on a lot of specific things about their computer at that particular moment in time. And so when you kind of take those programs and take that data, and you then kind of address them somewhere, you try to run them again, something doesn't work. Something went wrong, the program changed, the program happened to have some inclusion into, for some reason, into something that was linked by some location address that changed, and so everything is a mess. So this is where content addressing can help a ton. If you can content address all of the programs and all of the code involved in that thing, and you can kind of completely sandbox the thing to not make any kind of network accesses beyond anything that you content address, then you can end up with completely reproducible objects associated with science, where you have a paper, you want to run some computation to produce figures, or you want to run some computation to produce some cleanup of the data or whatever. You can do that by content addressing the whole thing. And so through this, then think of enhancing this kind of stuff with then kind of all the notebook-style computation and large-scale jobs, large-scale pipelines, and so you can do massive-scale data science. I think that this is, I would strongly suggest one of the main applications that this whole community in computer over data focuses on is this massive-scale data science because it tunes perfectly to the job type. So you want to be able to compute over public data, public commons. In some cases, you want private data, but the privacy of the data is kind of different than, say, live social network data or something like that. It leans on asynchronous data pipelines, which is what computer over data networks are going to do really well initially. It lends itself well to kind of these public identifiers like CIDs and so on. So kind of really focusing on this set of tools and set of use cases will help a ton. So I want to draw attention to this. And then the other one that I think is really good low-hanging fruit, when you look at large-scale engineering efforts to build things like programming languages and browsers and so on, you end up with these massive-scale testing infrastructure that test the performance of these systems to enable thousands of people to contribute code to these large-scale open source projects. And this is another example where scheduling jobs would be perfect. So imagine being able to run massive scale CI across these computer over data networks where you can, some new version of Bacalhau comes out, some new version of IPFS comes out, some new version of whatever program you want, and you can run it in CI at a massive scale, way larger than whatever the current CI systems give you. And what's better, you can test it in home settings. So you don't just test it in the cloud where you have these very weird type of environments, very different from kind of home settings, but you can actually go and test it in people's home computers in real network conditions, test it in phones, test it in those kinds of environments. And so you can imagine being able to build kind of a proper R&D test network that can properly get us like massive scale performance wins across all these systems. This is one of those cases of like you build a very high leverage product that enables you to then build much better other things, right? So if we build this kind of massive scale testing infrastructure first, then that will enable us to build all of the other use cases much easier. Because that'll just feed back on itself and improve all of the tooling and all of the components, because it'll right away tell you like what's working well, what's not working well, and so on. Highly recommend exploring, if you're interested in these use cases, highly recommend exploring the testing infrastructure of Chromium, Firefox, Rust, and Go. Those I think are some of the best ones that I've seen, and they're massive scale, especially Chromium. I haven't yet been able to find this page on the bottom right again, but it was in there somewhere. And as an example, they ran thousands of different benchmarks. For every single commit, they ran thousands of different benchmarks to show you whether or not like your particular change decreased or increased performance across tons of different platforms. And like that level of CI is what you need to make sure that like as a developer, you're improving the product and you're not accidentally breaking it or making it worse. So if we build that kind of system, which, think about Bacalao, like this is perfect setting where, you recruit a network of hundreds of thousands or millions of computers across data centers, homes, a bunch of other places, and then you submit a new version of Bacalao and so on. You then like test itself. You use Bacalao to test Bacalao. You deploy a new version to a bunch of these systems. You run some workloads. You test it, and then you kind of return the results. You produce all the profiling and so on. And lo and behold, like you have effectively built not only a thing that improves your product, but effectively is the same tooling that you need for this other use case around data science, right? Because a lot of this kind of profiling and reporting and so on is very similar to the massive scale data science. So these are like the two main use cases that I would kind of focus the whole community on. There's a bunch of other stuff like again like video and media and so on that will also be really valuable, but I think they won't be as valuable as these two. There's one around like CI, and let me see if I had it here. One other thing I'll mention is developer tooling. So think of all of the code on GitHub and containers and VMs and so on. Like all of those objects benefit tremendously from content addressing and need a lot of processing as well. So like we're talking about CI here for large scale testing. A subproblem of that is just doing basic CI over a thing. So you can build a decentralized CI network today with something like this as well. Cool. So here I want to kind of just speak a little bit about focusing on delivering impact. So for these kinds of use cases, focus on the core users. What do they need? What do they need right now? What do they need in the next 1 or 2 quarters? And build those features. There's a ton of interest on these programs and systems and so on. And that interest, that demand comes with very specific requirements in terms of performance, requirements in terms of features, in terms of threat model, in terms of incentives, and so on. So let's tune what we're doing to solve those problems early, as opposed to kind of like maybe like shinier use cases that are maybe further down the road. Let's kind of focus on the demand that is here now. Deliver impact in those groups, for those groups kind of quarter over quarter, and so build our networks to, over time, kind of grow with those communities and keep bringing more and more communities into our network. Cool. I'm gonna, since time is short, I'll open for Q&A now, and I'll maybe take questions for 5 minutes, and that's it.
So hi, thank you for the talk. This is very interesting. My question is mostly focused on the challenges that on the research challenges that this compute over data exists. So I'm a PhD student. I'm working on computations in general in decentralized networks, and achieving this is, from my perspective, is very, very hard. There's a ton of different little challenges that you need to address to do this. And my question to you is, how do you see, or for you, what are the challenges in this environment that you see that need to be resolved, like first?
Yeah, I agree. So a lot of this stuff is really hard, and that doesn't mean that you can't do it. It just means it takes a while. All of what I'm talking about today is stuff that a lot of us have been thinking about since 2014, 2015, and we built a bunch of the tooling underlying that was needed. So we built IPFS, we built things like Filecoin, we built things like libpp, and now, in the last year, we've finally been able to get to the computation part Now we're building that, and now we're sort of like ready for the scale. And just kind of like, big things have small beginnings. Like, look at the scale of the Falcon network is in a year and a half we went from, in 2 years we went from 0 exabytes to 17 exabytes. An exabyte is a lot. It's a lot. So if you can put together an exabyte, like we can solve compute over data. Like this is coordinating thousands of people around the planet and a huge like supply chain build out to enable this. It's a way harder problem than doing the software of scheduling and so on, right? So also very hard, but has been solved by many groups over the last 10, 15 years. It's a new setting. Decentralization definitely brings its own sets of challenges and so on, but it's like very, very solvable. This is not like you don't have to we're not trying to pitch scheduling compute over data in like the 70s when it was like first getting started.
Okay,
so solvable. In terms of I guess your question was kind of like what challenges do I see right now? It's this stuff. It's like kind of go through each one of these things and like make sure that you have good versions of these, and you use kind of like the latest and greatest stuff. So WASM is a pretty awesome setting. You can do a lot of the computation there. Not all of it. Some stuff you need like access to the local host OS, or you need access to the network. Maybe you can use WASI. Maybe WASI is not good enough yet. Maybe you have to like go and contribute to WASM in order to like get the interfaces to work right, to like so that you can use it. And then there's it's just a ton of like work that we have to do to kind of knock out all of these things. And then once you're done with this common part, then you have to do your specific network setting, right? You have to go and like if you're doing zero knowledge or fully homomorphic encryption, then you have to like do that. But by the way, I would say the optimistic settings are going to be way easier. So like just start there. Just start with optimistic computation, where you kind of the worker node kind of commits to the job, runs a computation, commits to the result, and then later you can sample that and rerun it and check it. And you can use staking systems based on that to get really good guarantees. Now it solves verifiability, but not quite privacy. Privacy is way harder. There you have to figure out like, yeah, we won't get into it, but the merging of like compute over data with incentives with Crypto Econ Day and so on, like think of that being like a very strong theme next year as we kind of figure out how to run these things.
So I'm very excited to see Bacalhau partnering with BOINC and getting a lot of the BOINC projects in, hopefully, to some more distributed systems. I'm curious about your perspectives on why we need blockchains when it comes to distributed computing, because a lot of the questions we get from researchers and people who do distributed computing on something like BOINC is, okay, but why blockchain? Why not database? Or any of your perspectives here?
What is database?
Just referencing the old, why do you need a blockchain? Why can't you just use a database?
Yeah, I'm just like I'm asking like a fundamental computer science question. What is a database and what is a blockchain?
You tell me.
So a database is just a set of data with the ability to query it over time and mutate it over time with some strong guarantees. You want to build a log of the operations that you're doing, and so that you can kind of over time accumulate the set of operations that you're doing over the data, and you can then query the thing. Now, it happened to yield a specific set of software components that we associate with the word database that doesn't give us public verifiability or doesn't give us public computation. It just kind of, it's a trusted private setting. Blockchains are a system of software that enables you to aggregate a bunch of data together and create a log of operations that are mutating that data that give you public verifiability and are tuned for the public setting. They're both the same kind of thing. They just come from different families of software development. And the point is, like, these are merging. These fairly soon you will see blockchains that are going to scale to trillions of transactions per second. And so and which will support SQL and will support like all kinds of these. Like the blockchain world kind of had to kind of backtrack a little bit from the trusted setting to arrive at this public setting. And now we're bringing all of the knowledge from distributed systems and databases and so on and programming languages to speed up blockchains. So the broader answer is like these private settings give you a ton of problems on the road. They just sort of like lure you into this false sense of security that you fall into, and that's what leads into like bad reproducibility for science. Things don't run later on. You can't have a commons. You can't compute together over the same data. Like if you're going to write a paper as a scientist, if you're going to write a paper, where are you going to address it? You're going to address it at like Elsevier. You're going to put your data into like some repository that's going to start paywalling people or like preventing access. Like hey, that's bullshit. like be a better scientist. Like get your data out in a public setting. Put the data such that it's accessible by everybody in an open access way, and pick systems that are gonna give you like super low cost, high scalability computation that's oriented with broader public access, right? So that's the broader answer.
Thank you.
Hi, you mentioned DeSci. I mean, you just mentioned it there. What do you think is like the quickest win, like the lowest hanging fruit that Web3 can offer DeSci that scientists will adopt and say, like, this is a great use case? Because I guess we have IP NFTs, but they haven't really been proven in court. And this, like, the data side of it seems like sort of the lowest hanging fruit. What do you think?
Yeah, so look, there's a lot of different projects in DeSci. Like, 1 second. So I'm not going to give a whole other talk, but like there's a talk that I gave recently that kind of goes over DeSci and so on. There's a ton of problems with academia and how science works today in academia. And I think like first and foremost, what DeSci can really help with, aside from all the computation stuff, is just funding. You have better funding structures that are much more kind of community-oriented and regenerative. And it might sound like, to a lot of people, it might sound crazy. But let me find this graph. It's like, yeah, so this is like the whole R&D spending of, say, on the left side is like most nations in 2020, most nations that do large-scale R&D, and on the right is like the US's budget specifically in like, $2020. So the graph on the right is not growing with the economy of the US. That is a serious problem. Like, this is why things suck today. If we had kept, growing the R&D budget in the U.S. relative to the growth of the economy of the U.S., I need to get another graph that shows like, GDP of the U.S. mapped against this. In a sense, you can think of like the amount of money that we're spending in science as decreasing every year because we're not keeping up with the GDP growth. And so like that's a disaster. And then on the left side, the U.S. is one of the largest spenders in R&D in the planet. So that's like even double disaster. Like not only is the US like decreasing its spending, it's one of the largest funders of science and R&D. So we have to like solve this funding problem. And turns out like blockchains give you the coordination primitives, and $70 billion a year is large, but it's not that large. If you have crypto networks that are hitting 1 trillion or 10 trillion in terms of value, you can start being able to afford funding of science and R&D at the scale of nation states. So that's kind of like the larger kind of crazy long-term vision. So think of that as being relevant like 10 years from now or 15 years from now. But kind of like even before that, you already have a bunch of kind of smaller scale experimentation that can happen. Separate from that, there's this whole other stuff around just kind of like the reproducibility of the artifacts and so on. So you mentioned IP NFTs. Like I do think that those are like extremely good experiments to be able to change the way in which IP gets generated and gets funded, moves back in. You need to change the incentive structure of how we get kind of results in the market, and we bring back funding into funding R&D. And so things like this are really good experiments to try and do that. And then HyperSource is another. I'll plug that. Then there's a whole other part around like just organizing people and organizing the work. So think of GitHub as being super, super valuable to all of science, but it's not even tuned for science. You can't even do the type of processing in GitHub that you would like to do at large scale kind of scientific type of computations. So being able to do that, that's a really good part for DeSci, where like you can start doing those kinds of operations. And then you can think of like, as you do all of this work, you can sort of like think of like structuring the credit attribution graph of all of the people working on this and so on, and that like that gives you, again, feeds back into funding and long-term rewards and so on. So yeah, like there's a lot to say here. Maybe the computation piece can help with how we do the science and how we make the science reproducible. Like just get to the point where like when you read a paper, you can get access to the paper. Like you don't have to be paywalled. And when you see a figure or you see the data, you can click a link and get the data, and you can click another link and run the program in your computer or a compute network or whatever and reproduce it. Like it's that simple. Today, unfortunately, though the number of papers is growing exponentially, most of those like you can't check, and that's that's not what science is about. Science is about like really getting to being able, like taking no one's word for it and really being able to test all the things. And so getting to reproducible science alone would be a massive breakthrough for DSci to do.
Cool. So clearly you guys have I've talked to people, you guys have put a lot of work into cybersecurity. I mean, so that's like code hardening and Dockerizing to protect the service providers, to protect the client. You have all of the verification things and the other stuff on the Juan's triangle, which that's cool. Nice. Have you thought about the safety of others, as in, this looks like a giant botnet?
Yeah.
Have you thought about controls against that don't really just hand the key to people for censorship?
Yeah, it's a great point. So the internet is a huge botnet. So yeah, the one part here is you can use a lot of the sandboxing that we've already built into cloud systems and browsers. So the cloud and browsers both have had to build a bunch of this sandboxing in VMs to be able to sandbox and program from like being able to access other co-located programs and so on, and sandboxing in terms of the networking to be able to rate limit, use, detect abuse, and shut it down. So the good news there is that it's not new ground. We just have to apply a lot of the techniques and solutions that have worked already. But that's a lot of work. So that isn't, I don't think that's a lot of that is done yet beyond kind of the basic sandboxing that you get out of things like WASM and things like V8 and like the VMs. But all of this kind of networking, sandboxing, and so on, like we should be learning from the browser, because the browser has a lot of really good defaults, and you can even use things like Electron. And B, we're going to have to blend cloud and browser type sandboxing, and that's a bunch of work. So cool. All right, thanks everyone. Great to see you.